Welcome back, everybody. Fall 21, Test 4, Part 4. Provide a mechanism that accounts for all products, A through D, A, B, C, D. And a lot of points. Circle the major product, explain your answer. Yeah. Ladies and gentlemen, this is a analysis question with a mechanism as well. It will be your question 4, which is, this is really the second question in part 4. There was no question 2 or 3 on that test. So this is the second question, even though it's numbered 4. Your second question will be an SN1 or an SN2 or an E1. I should be saying and or for each of these. SN1 and or, SN2 and or, E1 and or, E2 and or, NGP. This will not be NGP. For the NGP, I give at most 2 products. So this got 4. Some of them, the bromine's been replaced by a group. That's called substitution, right? And the final one, D, there's a new pi bond. What do you call that? This is your second chance today. Elimination. And do you remember that elimination is a minor result for every SN1 reaction? It's called E1 minor. Here's our analysis to prove such a thing. This here is a tertiary RX. You better be thinking SN1. Poor new, you really better be thinking SN1. Polar product solvent, everything says SN1. So SN1 with E1 minor. What's the first thing you do in any mechanism ending with the number 1? What is the buzzword for SN1 and E1? The carbocation. You beat the morning section by 10 full seconds. Thank you. Okay. It was hard getting that out of them this morning. It was morning. It's early in the day. I don't know. You got to make a carbocation in SN1. My apologies to the morning section. Didn't mean to throw you under the bus like that. They're a good class. They're both good classes. Okay, we got a cation here with a double bond up here and a F. You'll probably be able to see one of the products that comes directly from this. And on my screen, I can't see all the products because my picture's in the way. Okay. So I'm pretty much seeing product A happening pretty soon, aren't you? How do you get that O with the isopropyl on the molecule? Where's that O come from? From the alcohol. Please don't take the H off until it's a strong acid. Right now it's a very weak acid. Don't take it off. That's not how pKa works. Make sure that arrow goes all the way to the C. And you have something that looks like product A. It's related to product A. You've got O, H, isopropyl. I need something that's going to grab that H and make it into product A. You might want to use Br minus, and I probably wouldn't give you a hard time, but it's not as good a base as isopropanol. And isopropanol, I hope you know it's the solvent too, right? There's no other nucleophile listed. It's the solvent. So there's a lot of it. Please use isopropanol. It's a better base. We've had this discussion with oxymercury, or not oxymercury, one before that. Anyway, a long time ago, we had this discussion. I just can't remember. Use another isopropanol. Grab H, neutralize, end of story. BR minus is not wrong. It's probably not real. There's only one BR minus you ever made here. It's in that first step, right? Like one. There are moles upon moles of isopropanol floating around, right? It's a solvent, okay? And my arrows, you know, there, a little better. So product B, I think the ring opened up, right? Just look at B. You need to copy the cation because what you showed was the cation doing this. The same cation can rearrange. Guys, cation rearrangement, carbocation rearrangement never goes away. Doesn't matter how you made the cation. Rearrangement is an option. So we got a version of this cation. You're going to need 4 versions if you want to go ahead and do that. I don't know. It's not fair if I try this. Not good. Somebody was telling me, don't copy paste it. They can't copy paste it. I can copy paste it now though. So I would go ahead and do that on your test too. If it's an SN1, draw as many cations as you have products. Got it? There's 4 products listed. I'm going to need 4 of the same cation. There's only one cation possible. And which rearrangement is going to work to make that ring bigger? How about this one? All the way to the C. You want to see my numbers? And there's 1, 2, 3, 4, 5. Six-membered ring didn't change. Copy it. This bond didn't change. 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 This bond moved over here and it left behind a cation that's amazing. This is a tertiary benzylic. It's like allylic, everybody. I'm writing allylic by mistake, of course. Cation. Stability, this is new for you. I never said this before. Roughly equal to 3 plus 1.5 equals 4.5 degrees. You add 1.5 for allylic or benzylic. You want more of this? Look at this morning's videos when we mentioned this. So of my 2 cations, this thing is vastly superior. Ring size got better, and the cation stability with hyperconjugation went up, right? This is equivalent of a 4.5 degree cation. Wow. So I'm really thinking this product is going to be major league. Let's put some dots here just so you know there's a carbon there and a carbon there. This is looking a lot like B. I'll draw it a little nicer. How do I make that into B? Well, same way I did before, right? You need another isopropanol. We have a never-ending supply of isopropanol. And I'm just going to go ahead and circle that product. I mean, you guys would have probably instinctively done this without even doing the mechanism, right? You see that ring? There's no four-membered ring anymore. That discussion's getting old, right? And do we have to do an explanation? I think we do. Circle major, explain. So you're going to do your explanation right here. Explain. B. Tertiary cation. Tertiary benzylic cation. More stable. Plus torsional and angle strain. Don't say they're eliminated. They're greatly reduced. Greatly reduced. I'd say that second part's more important. That second part, more important. Okay, good. This is just kind of notes for you for future use. So we got two of our products. What about product C? What moved to get the skeleton like this? Okay, the pH, the phenyl? The phenyl, yeah. I agree. It jumped over next door. We need a, yeah, we've got our copy here. Move the phenyl next door. You're still having the angle and torsional strain. Not a great cation. And isopropanol again. HO isopropyl.
Other question?
Yeah. It's a carbon. We can move methyls, ethyls, phenols, isopropyls, hydrogens. No, it's nothing about heavy at all. No, it's very happy moving. It's a happy mover. Yeah, phenols love migrating. It's their time of year right now. I think that's the third product, conjugate acid. There's the third product. And we'll see if we can get it in there. Need your isopropanol again. So we're doing the same thing over and over. We're hoping this mechanism shows up, right? And this is going to go straight to D. Oh, I don't want arrows touching and stuff. How do you get from there to there? It's E1, by the way. You've got your cation. You've got to think about a beta H. Now, the definition of beta changes a little with cation, but it's not that different. The cation is the alpha, where there used to be a leaving group. Think about it. It's the same position, right? When you had the bromine on there, you called it alpha. Why not call it alpha now with a cation? Where's beta? Well, look at the picture of D, please. You can't just randomly pick an H. The H from the top right. Draw it. Remove it using the solvent. Make pi. That's it. Big picture. Whole deal.